Hello and welcome to the lecture Generative Modeling. In this lecture, we are going to introduce what is generative modeling. Then we try to understand what is the difference between generative and discriminative learning and what are the types of generative models. Now, we are trying to understand what is the basic understanding of generative modeling by virtue of a kind of model architecture. So here it is a very simplistic diagram of a generative model. Now you can see here that generative model is basically a neural net that generates some generated data or kind of a new samples. So from where we start, what we have been given? We have been given an unknown distribution D like this. This is a real data distribution and that has been given. And this data distribution we don't know, because that's why it is called unknown distribution. The D we don't know, but we know the D by virtue of these samples. So what is our objective? That our objective is to create or generate these kind of samples, but not exactly these samples, such that samples are basically going to sampled or is going to or belongs to some distribution. That distribution and this distribution is very similar. That is the main agenda of generative modeling. So from where we start, we are given a real data distribution. Let it is a D. Okay. So and our objective to train a neural net this. So what is the input to the neural net? That is interesting. So it starts from a random noise, that this distribution P of Z is belongs to this random distribution. It's a random noise. Now this noise is input to this generative model, and this generative model is basically a neural net that generate samples which belongs to our data distribution, let's say D bar. And what is our target? This D bar, what is basically consists of the generated data samples which is generated by this generative model, that is a neural net G, when this random noise is taken input, and this D bar should be very close to this value. So this loss, what are the loss is being calculated, but what is our intention, what is our target? That this data distribution and this data distribution should be very close or very similar. So loss is basically the statistical distance between D and D bar, these two distribution. So if we minimize this loss somehow, then generally this distribution or these data samples belongs to D bar is becoming close to the D. And essentially the samples, the generated samples will become more and more alike the real data samples. So generator take a random noise Z and generate D bar from this. So this is the total picture. I repeat, a generator model, it wants to generate such samples that it is these samples belong to D bar, and D bar should be similar to a given real data distribution. So the generative model, that neural net, the input is coming from a random noise, and we generate these samples, and these data samples is a real data distribution. What is the goal of generative model or neural net? To minimize the distance between, or statistical distance between these two. They will try to such. So loss is computed in such a way that is statistical distance between these two data. So we minimize loss. That means these two distribution become closer, and this loss is backpropagated model. Okay, so this is the generative modeling, the way it is. So we can understand that neural net is trained such a way that it can produce data sample of the distribution d bar from a random noise. That what? And what kind of data sample they want? That this d bar, this distribution should be close to this given real data distribution d. The neural net is optimized to the difference between the actual sample distribution d and the generated sample distribution d bar is reduced. So what is the optimization criteria? What is the loss function? Difference between these two, or statistical distance between d and d bar. And if we minimize this loss, then definitely these two will come closer. What does this mean? That means the data distribution d bar become close to the d, so that the generated data samples is more alike or more similar to the real data samples. So what kind of statistical distance we calculated here? We can use, for example, L1 norm, L2 norm, something like that. So after convergence, generator can generate new samples. That is very important to understand again. Once if you see this, that this is a real data distribution, fine. But what we are generating, these samples are not exactly similar to this, some of the samples. So these samples are different, but the distribution they belongs is very close. So this blue samples for this, it is from d bar, it is generated data samples. This green sample is a real data samples. These two samples are not same, they are different, they are new samples. That's why it is generative in nature. It is not reconstructing. That will be very important to understand. We are not reconstructing the data samples. Rather, we generate the new samples so that the distribution of these samples, new data samples, and the real data distribution should be very much similar. So that's why generator can generate new samples which is very close to distribution D but not present in D. So those samples which is generated is not present here, and that is the major understanding of generative modeling. So what is the basic difference between discriminative learning and generative learning? So what we have discussed so far, the discriminative models are trained to find the conditional distribution. That this is a parametric model, that's p theta, that given x, trying to find the y, that by maximizing this log of p theta y of I given xi. That is the basically discriminative model. So what it basically is, this is dog and is a non-dog. So what does this mean? That we want to find out this decision boundary, that discriminating, that separating the dog and non-dogs. An interesting situation, what is that giving X is the dog, what is the probability that Y use this image? So it is very high, 0.95% confidence that this is a dog. That after training the classifier. So discriminative models actually do learning by discrimination. That is, and this statistical definition is this. On the other hand, generative models are trained to generate samples from a distribution which is similar to a given distribution. That a distribution is given and generative models try to train such a way that it can generate samples from a distribution which is very similar to this given distribution. That's what we have seen earlier. So let data be drawn from an unknown true distribution. Let P data xy, that is xy, that is data and the label this is coming from this distribution and it is unknown. So a generative learning model learns parameter theta of a model of P theta xy. This is basically this generative model, such that this distribution is basically very similar. And if you know this joint distribution, we can generate label, we can generate data, we can unconditional samples. So generative learning is the estimation of the joint probability distribution P of x comma y of this data. We have to learn theta such that we can. And how can we do this distribution? By virtue of this joint distribution can be written as this P of theta y and y P of theta x comma, where this P of y is called class prior because this is probability, and this P x given y is the class conditional density. So this is the statistical understanding of generative model. So very simplistically, we try in generative modeling, we try to estimate this joint probability or this joint distribution such that we can generate it. Okay. So this is the discriminative. Now there is mainly there is three types of generative models. First of all, explicit models. What do you mean by explicit density models? They are true density estimator. That's it, really they estimate the density. So autoregressive model, that we have seen the language models. Normalizing flow, variational autoencoders, these are explicit density models. Okay. You see next that this is the explicit density. We will come in here. Next is implicit density models. These models do not compute this density explicitly. So one direct approach is called generative adversarial network. Okay, that essentially samples, not compute the density explicitly. Another is called score-based diffusion models, or score-based or diffusion models. This is an implicit density estimation through or via score estimation. So denoising diffusion probabilistic models, DDPMs, and score matching models, examples of this. So these three very important generative models that in our course we touch upon some of them, and autoregressive models, one of these that we will understand in detail. Variation autoencoder, that will go in with detail. Generative adversarial network, that is implicit density models, and it's very important to help me understand this. And some diffusion models. Okay, now if you these different models, if you see that generative models is basically these two, explicit density model and implicit density model. And explicit density model, again, there is a tractable density. Why? It tracks density. And fully visible belief nets, NAID, MAID, pixel RNN, and this change of variable modes models, non-linear these are under tractable density models. And some will approximate density. That approximation is called variational and Markov chain. So variational is called variation autoencoder. It is also explicit variation autoencoder. Okay, that what we have seen. That variation autoencoder is explicit density. Now, implicit density model is a direct approach, that is generative adversarial network. What we have seen here is implicit density models. Okay, and there is some other implicit density Markov chain, that is generative stochastic networks. And this approximate density model is variational and Markov chain, there is more coordination. So this is as a whole the generative models. These are the basic models. We start with explicit density models. In explicit density models, we directly specify and learn probability density function p theta x and can evaluate the likelihood p theta of x exactly or approximately. So statistically, what we have seen, the density estimation, we are going to maximize this likelihood. Since it is a log, it is becoming some additive thing. So we are going to maximize this likelihood. We choose theta such that we can maximize this. That summation is equal to 1 to n is number of samples log of p of theta, p of basically this of these instances or samples, that we are going to. So an explicit density model defines a tractable probability density function. It somewhat we can, this probability density we can tract, or we can also approximate. It allows likelihood computation by this, and it is usually trained by a maximum likelihood estimation or bound on it. That's exactly what we have seen here. this explicit density function, we can use a tractable density or approximate density. So tractable density is basically maybe of, these are the examples, fully visible belief nets. This net made this kind of pixel RNN and change of variable near IC, something like that, where the density can be tracked. Somewhere we approximate this density. Now when we see this variation on autoencoder, that we can understand how we are going to approximate it. So explicit density distribution is tractable and approximate. So here also you can say generally explicit density model defines a tractable property function that can approximate, allows likelihood computation, and it usually trained by a maximum likelihood or bound. Okay. Now it is two main categories, that is tractable, that what we have said earlier, tractable with exact likelihood models, that is the autoregressive models. Now what is autoregressive? Autoregressive means that we can understand autoregressive very well using the language model. What is it? Given a sentence or given a set of words, we can predict the next word. Let us again take an example that I am a good boy. Now in this sentence, that autoregressive is that if I am a is already we can get, then based on seeing this part of the sentence, how we can say that what is the probability or how we can predict and what accuracy would predict, say good. So on the other hand, we can say that we have to train our model in such a way that seeing this I am a, we can predict good the next word correctly. Now in this case, how we can get this? We can factorize density using this chain rule. Now you can see what is of xi, probability of xi, that given x of less than I. Now you just see what is probability of m, that only before only one word. So it is x2, it is x1. So after I, what is the probability of m? Next is what? It is multiplied since it is multiplication. Next what is coming? What is the probability of A giving what is the previous words I and M? Then what is the probability of good? I am good where it is given I am A, and so on. If we keep on multiply, we can get this probability. This is the autoregressive model. And how this conditional probability is modeled? By Uniprolite. For example, pixel RNN and pixel series. So these are the autoregressive model, and it is tractable, exact like. Another thing is called latent variable model, that approximate likelihood. This is called variational. This is the example of this kind, variational autoencoder. So what we know about autoencoder, we'll see later in details. But here, just briefly, what do you mean by autoencoder? That reconstruct the input. That is called autoencoder. But the question is, the normal autoencoder, is it a generative model? Because please try to understand that generative models generate new samples. Those samples are not in the training samples or given samples. But normal autoencoder reconstruct the input. That means it is not generative in nature. But how we are going to make a normal autoencoder to a generative model, that is the main understanding of variational autoencoder. So in variational autoencoder, what generally we do, in normal autoencoder, our latent space, after encoding what space we get, it is generally the values. But we will see when we go details that in variational autoencoder, we generate by our encoder produce a set of density functions, so that some values can be sampled out of this density function, and that change makes the autoencoder the generative one, and that we're going to call the variational autoencoder. Okay. Now our next thing is implicit density models. So in implicit density models, what happened? That these models do not compute the px, this probability density explicitly. Rather, they learn a sampling procedure or match distribution indirectly. So the main examples, one of the most popular example is generative adversarial networks. Here what we're going to do, that there is a generator that generate the samples from a random noise, that is generated samples, and there is a given a set of real samples. There is another neural network that is called discriminator that try to find that these samples which is generated by the generator, that is called fake, and what is coming from the real distribution, it is the real. The discriminator, which is also a neural net, that is going to understand or learn to distinguish between this real and fake. So what is the job of discriminator? To understand this particular thing is coming from real or coming from generated. Generated is called fake, and accordingly provide the adversarial loss. So there is a two neural net. One is generator, one is discriminator, and it is competing to each other. Generator is one side, try to generate a samples which is very look like, very similar to the real sample, so that discriminator can be pulled. On the other hand, discriminator finds to distinguish between real and fake, so that generator can generate more realistic based on this error. So this we can say when we put the loss function or in details, so this is the min max game kind of thing. But they never compute this density px, rather they sample it. So they are generative models without explicit density estimation. Okay. Now the final thing is diffusion model, score based models. So this example is denoising diffusion probabilistic models in GDP. So here this score matching model, this estimate the score function by virtue of this x log of px. They don't estimate the density directly, rather they estimate its gradient. So it's basically its derivative of this. So they perform the implicit density estimation by score estimation. That we'll see when we'll discuss the diffusion models. So in summary, in this lecture we define generative modeling, and then we try to understand the difference between generative and discriminative learning, and then we'll discuss some different types of generative modeling. In the next lecture we start the generative adversarial network properly inverse scan. Thank you very much.